Hello and welcome to today's webinar. My name is David Cash. I'm a member of the marketing team here at Mountz. I'm glad that you have taken the time to join us today, and I hope you find something useful out of today's presentation as we look at 5 ways to improve process efficiencies and fastening automation workflows. And so typically when we're dealing with any type of process, there may be some repetition that happens, and that can really be an issue because of the fact that it is repetitious. It is a little bit mundane, perhaps, and it doesn't keep the person interested in what's happening. And so when it comes to fastening repetition, this could be a situation where you have multiple operators doing the same type of fastening processes, but maybe at different values of torque within a specific line environment that may be dealing with. And the real risk to that is the human error that happens with those types of tasks, where the operator may not be paying attention as well as they should, causing fastening errors where you may get fasteners that get skipped, fasteners that don't get fully seated, fasteners that are simply just not torqued correctly, and this may cause some additional problems down the line. And so if you are a familiar with lean manufacturing or the TPS, the Toyota Production Systems, this may look pretty familiar, but the dotted line that runs across our graph here is the ideal capacity for production within a line or product from beginning to completion. And our waved line here results in different transitions throughout that process, which is more representative of what's really going on within the process itself. And so if we take a look at what this actually represents is everything that is above our dotted line is our Murray. And this is overproduction. This is things that are overburdened. And everything below the dotted line is the muda, or what is classically labeled as waste. And that waste can be a number of different things. It can be the waste of transportation, the waste of time, and things like that are going to affect our process. And so the distance between those two is the Mura, and so if we can look at certain areas within our production environment and we can flatten the distance between the what would be the waste and the items that may be causing overburdenness or overwork or bottlenecks, then we can get a little bit closer to our capacity, where we are creating and fulfilling things as they are needed, when they are needed, to be as efficient as possible. And so that's going to kind of lead us to our poll question for today. And it's a pretty simple yes-no question. And it is, do you have multiple torque settings within the process steps in your fastening application? So I'll give you just a few seconds here to go ahead and answer that question. And then we'll go ahead and move on through our presentation. I'll grab just a quick drink of water and we'll be right back. All right. Thanks for participating in that. And the majority of the answer is yes, that we are having multiple torque settings in our process steps. And that kind of leads us to why we should consider workflow automation for our particular processes. And obviously that's why you're here to learn a little bit more about that. And so if we are dealing with applications that have a repetitive series of fastening tasks, or we want to increase our production rates, we want to increase the savings by reducing tool costs. If we are looking to optimize the workstation cycle times, improve our product quality, and enhance the process of reliability and efficiencies. These are all good drivers to look at how we can use process automation and workflows to go ahead and accomplish those specific goals. Now, the benefits of the workflow automation kind of go hand in hand with some of the actual operations, but the benefit is that we allow the application or operation to be streamlined, where we can help to eliminate some of the operator influence that may be associated with that particular application. We then have visibility and traceability by using certain types of automation tools that give us the ability to consolidate different opportunities within the use of tools to help satisfy some of those workflow automation goals. And so let's go ahead and we can just jump right into the 5 ways that we can improve our efficiencies through workflows. And the first one is going to be able to error-proof the fastening process. And if you are familiar with the other or kind of a companion Japanese philosophy with manufacturing is going to be the poke-yoke, which is error-proofing the process. And error-proofing basically means it's giving the operator the opportunity not to make a mistake. So we can kind of craft the operator's behavior in a way that doesn't allow them to make a mistake. That's really important when we're dealing with torque. We want to make sure that our clamp force is correct, and we get that correct clamp force by ensuring that our torque control is correct. And in some of the other instances, we want to make sure that we hit all of those fasteners to ensure that correct clamp force. And this is done through the use of different process control devices through the operation with using an intelligent process control system, giving us the ability to not only help eliminate any type of error that will make its way through, but it gives the opportunity for the operator to go ahead and make the adjustment or correct the error right when it happens. So we have that ability to monitor what's happening during the actual fastening rundown to make sure that that gets done correctly. And this also enables us to have integration through line control devices, so that if a part may be locked until all of the fastening is done, that gives us that ability to have interaction with different line control devices as well. And there can be other items such as light trees and other types of devices here. So that would be the first one, would be error proofing the fastening process. Next is going to be being able to collect data from what's happening during that process, and how we can automate that with being able to grab certain data from the fastening, what may be happening during the actual process. So if we do have that fastening data, it does give us the ability to look at what may be happening in our Mura state from our low to high wave there. And this gives us the ability to make data-driven solutions within what we are trying to accomplish. And that could be looking at the fastening data from one operator to another operator, could be fastening data from what may be happening from one shift to another or different days of the week, and things like that. As you're looking to get a little bit closer to your capacity line, what does that look like? If you have data to do that, then it does give you that ability to make intelligent decisions about the process that you're dealing with. So that was number 2. Number 3 here is going to be using a transducerized electric torque screwdriver. And that simply means that there is a built-in sensor in the tool that is constantly monitoring the actual torque output that is being generated by the tool. This is done obviously in real time, giving us our ability to do our previous key there, which was collecting that data. And so as it is measuring, there are other things that we can add on top of that. And we'll take a look at that in our demonstration process, but that helps to utilize what data that the tool is actually producing that we can control and manipulate, giving us, again, documentation, traceability, for what is actually happening during the actual process. And that leads us to our 4th key, which is going to be process control, which is basically a set of standardized tasks that we are dealing with. And in this case, we are looking at being able to program assembly sequences for the operator that will allow them to use the same tool, but allow tolerances and settings for each fastener that they may be required to assemble, but may require different tools if they weren't using a transducerized smart system. But we can have tolerances and basically sequences that will allow the tool to make an adjustment based off of the fastener that they may be using to ensure that the process, again, is streamlined or is efficient, so that we aren't creating those bottlenecks or that within our process, giving us the ability to have multiple fastening tasks with the use of one tool and one operator. Again, this gives us the ability to minimize the use of different workstations where we may be able to combine those in saving tooling costs and also operator costs as well. And then the last one is going to be the fastening automation. And this, again, couples along with some of the other items that we've talked about, but it does give us that ability to have an intelligent process with the use of our automation, where we can replace different manual processes that may be limited to maybe just a one torque setting style of tool, whether that be a manual torque screwdriver or an electric torque clutch tool. So those items we can again help to automate with our fastening, where we have a lot of control over what's happening during the rundown, after the rundown. We do have the ability to communicate with digital input and output devices. Again, those can be communicating different things at different points throughout the process. Could be a PLC or a line control device where a part comes in, a part doesn't leave until it's fully completed, and then the next part is ready to go. So all of those different items can be accomplished with using a specific fastening automation and those tools that are available with different types of settings and uses. So to recap, our quick 5 items here. First, if we can help to error-proof the fastening process to ensure we've got the correct clamp load that we're looking for, giving us the ability to control, or excuse me, collect the data that's happening. And we can collect that by using a transducerized tool with a good process control, and then finally fastening automation. Now, that was a pretty quick rundown of what that is, but we can accomplish these things with the use of a DC controlled tool to help with our different workflow operations. And so that's going to lead us to our demo portion for today. And I'll be using our new MD22 tool. This is a really low torque value driving system. Those go from 1.4 inch ounces up to 97.3 inch ounces with different models here. But this is the system that I'll be using today to go over our different application scenarios where we would be looking at trying to solve different problems within our Muda or our waste or our Murray, where we're a little bit overburdened or bottlenecked in some scenario. And so we kind of talked about it a little bit, but when we are dealing with trying to consolidate our workspaces or workstations, if we do have too many of those, or we want to try to, again, be a little bit more efficient, we can do that with the use of the DC tool. Now, in this case, our particular tool here has 15 different presets that we can use. So in essence, we have 15 different tools, or we have 15 different profile strategies that we can use within our application. And there are several different scenarios, or there are different fastening tasks that we can use, or different strategies that can be implemented through the different presets. We also have two special ones, a multi-sequence A and a multi-sequence B. These allow us to actually stack different presets on top of each other that we can use in one rundown event. And these are a little bit specialized, but they can be used to help solve different types of fastening challenges. But we do have that ability to be able to use 15 different tools, basically, with just having one system. And so that can help to consolidate workstations for us here. Now, our next is going to be our fastening bottleneck. This would be our Murray state. And in this scenario, we have a fastener that may be a little bit long in length, and it's a really low torque value. And typically when we're dealing with lower torque values, RPM really plays a factor in how accurate we can be, especially at the low end, as we're dealing with trying to control inertia that may be happening when the tool shuts off, giving us some erratic readings. And so in this case, we're going to be looking at preset 1 here. We have a torque reading at 4.25 inch ounces. We've determined that 250 RPM speed is going to be ideal, giving us the ability to be very accurate at this amount. And so if we go ahead and run that tool down, or run a fastening down, you can see that that would take a little bit of time to be able to complete that operation. And because this is an area where we would like to streamline things, make it a little bit more efficient, that rundown took almost 4.5 seconds for us to accomplish that. We can use a scenario where we can run the fastener down during the thread engagement portion at a much higher RPM, and then allow the tool to downshift back to the seating RPM of 250 RPM. So if we come here to our free angle and free speed, or RPM, that's what we can do. And so this particular fastener is about 6,000 degrees of rotation. So let's go ahead and set this to 3,500 degrees of rotation, and we want to have 1,500 RPM for that portion of the rundown. So if we come back out to our preset, and now we go ahead and run this down, you can see that that was a much better and faster rundown, and we still were able to be at our 250 RPM right as the fastener is being seated. And that decreased our time there to 1,200 milliseconds, basically 1.2 seconds. So we shaved almost 3 seconds off of that runtime by using our free speed and free angle on this particular application. So that would help in that type of scenario. Now, the next one that we may be dealing with is a cross-thread type of issue that is going to help produce waste for us, whether that is damaged parts or something that needs to be repaired down the line. So let's take a look at how we can tackle a cross-thread issue with our unit here. So we can still work on preset number 1. Go ahead and log into the system in our parameter, and in our fastening menu, we do have the ability to have a soft start feature. So this can be set from anywhere from 0 up to 300 milliseconds. So if we set that to 300, that's going to give us a softer transition up to our running RPM. In this case, it's going to go quite quickly to our 1,500 RPM that we just set. There's also one other item that we can use, and that's going to be in our advanced section, where we can use our free reverse rotation. And what this does is it allows the tool to start in the reverse direction for a determined RPM and amount of turn, and that will then help the fastener find that first thread and then go ahead and transition into the fastening direction. So let's go ahead and we can set the RPM quite low to 75, and then we can set our amount of turns to just 0.7 of a turn, and that should give us a really good ability to have that fastener find that thread, and then it will then go into the fastening direction. Very similar to when you put a cap on a water bottle, you'll spin it backwards to find the thread. Same type of process here. So if we come back out and we go to our fastening here, now what will happen is, let's go ahead and bring this all the way out. So it will start in the reverse rotation and then transition to the forward rotation. So that can help with our cross-threading that you may see, giving us that ability to start the fastener in the reverse and then transitioning to the fastening direction. Again, we're utilizing the soft start feature with this as well to help combat both of those, or at least that one issue there. All right, the next is we want to look at how we can actually error-proof the fastening. And so if we did have a cross-thread event and the operator really wasn't paying attention, what would happen is the fastener would bind up, the tool would hit torque, and the operator may just continue to go on. Because the tool shut off, it hit torque, and they just keep going about their operation. But in essence, that fastener is not providing any type of clamp force for us within that operation. So how can we do that here? So let's go ahead and take a look at that scenario. Again, we can still work with preset 1. Now, in this case, to help guard against or at least detecting if there is a cross-thread event, come back into our fastening, and we can use our min and max angle requirements. So one, or just to back up here, there are two different types of torque strategies or fastening strategies that we can use. We can use one that's going to rely on the torque, and then we can monitor the amount of turn that happens, or we could go with a strategy that's going to allow us to set a certain amount of rotation and monitor the torque. So in this case, we're going to be using our torque control with our angle monitoring. And so we have the ability to set a minimum angle and a maximum angle. So what this means is within our fastener here, if it takes roughly 6,000 or so degrees to run down, we want to make sure that the thread engagement happens. So let's set our minimum angle to 5,000. And so if the tool reaches torque at a degree of turn anywhere below 5,000, we will see an error that will happen. And we can also set a maximum angle as well to help guard against stripping, or at least notify the operator if a fastener has stripped, because we can say if a fastener goes more than 8,000 degrees of rotation, then we would get an error there as well. So let's go ahead and we can come back out now. And if we were to demonstrate what would happen in a cross-thread type of an event, we can go ahead and use one of the fasteners that we've already done. That would simply just simulate the fastener binding up. And you can see that we have torquing during the, well, this said during the free speed, but again, that is going to notify us when we would have a cross thread here, but we were notified that that happened. If we let the tool run and it goes more than 8,000 degrees, you can see we had our angle over error. So that's how we can help, again, add a second layer to the error proofing process by monitoring the amount of turn that happens with the fastener. And then there is also one other way that we can help monitor the amount of torque. We do have the ability to monitor the torque percent limit. So whatever percentage of torque that we would get that would be outside of this percentage would produce an error as well. Again, just giving us another layer to be able to satisfy that for it to be considered a good rundown. And then finally, we want to look at another area where we can help to maybe automate the assembly process. And this would be us being able to set a fastener specific type of setting tolerances within the unit here. And so for us to do that, that would be considered, in our scenario, it's a model mode, meaning that we use a model to help set up our assembly. And so we need to put the controller into the model mode. So once I do that, we can come down here and go to model. Now, the model, we can have up to 15 different models. So right now we're dealing with model 1 of 15. Those models can be made up of the 15 different presets that we have available, and each model can have up to 20 steps within it. So in this case, we'll just keep it a little bit simple, but just to show you, if we wanted to change to a different model, we can come in and select that down here. Now we're working with model 2 of 15. So that's how we would jump from programming one model to the next. And so in this case, what we're going to do is we've got a simple 5 fastener assembly. We're going to be using preset 1, preset 2, and preset 3. And we have a specific count for each of those. So preset 1 will be 2, preset 2 will be 1, and preset 3 will be 2. And this will allow us to go ahead and do this assembly. Once we finish our first 2 fasteners, the system will automatically change to preset 2, and then automatically change to preset 3, and so on. Now, there are more operations that we can do within a model. You can add a delay in here. We can use input or output. We can also use a barcode in here to do some data collection items or tracking if we want. So there are more things to do there, but that's not what we're here to talk about. But nevertheless, if we come back out to our operation screen, you can see that things have changed here. We are dealing with models now. So we have models 1 through 15 that we would be able to select to use, but we're using model 1. Right now, this is using preset 1, and this is the first step in our fastening. And you see our count is down here is set to 2. So as we go ahead and go through this operation, you can see that the system is going to update after each fastener. So we'll go ahead and run this one down. All right. And our count has updated here. We're still on preset 1 at our first fastening step. And now we've changed to preset number 2 and our second step in our rundown. This one has a different torque value at 2.75 inch ounces. And now we've changed to preset 3, which has a preset value at 3.15. And the model is now complete. And then the system is set to go ahead and repeat, or you can control it to not automatically repeat, where you could select it with a different with a barcode scan, and it would change that model or assembly for if you had maybe a low volume, high mix type of scenario where you may have different items within your build that may change to different types of assemblies. We also have, with this torque arm that we are dealing with, you do have the ability, along with another piece of equipment, to actually make sure that there's only power to the tool in the correct operation area or over the correct fastener that needs to be used. the system will tell it which preset to use, and it will not count that unless it gets a good rundown signal back from the controller. But so that's how you can implement different automation types of to help satisfy your different workflow operations. And so with that, that'll lead us to the end of our presentation. And we'll go ahead, if you have any questions, feel free to put those in the chat, and then we'll go ahead and answer those. So Chris, do we have any questions?
Morning, Dave. One of the questions we had was, can you confirm again how many workflows or fastening sequence that can be programmed and stored with it?
So on the unit itself, there are 15 different models that can be made, or 15 different assembly processes that can be made up of the 15 different presets that are available. And then within each model, it can have 20 steps. So if you need to go outside of that, there are ways that we can program it to do that. But that is by default what we have on the controller.
All right, Dave, I think that's all the questions we have for today.
All right. Thank you so much for joining us today. And we look forward to seeing you next month in our next webinar. Thanks so much. Have a great day.